Hey YouTube, after having explored the graphs of logarithmic functions, what we're going to do in this video is we're going to basically confront the fact that a logarithmic function is indeed a function. And so they're graphs. Let's go ahead and make one bold statement about these. We say for any function that's just y equals log base b of x. The things we know about these are that they're of course inverses of exponential things. So clearly these things would be obviously true. We say that it has a vertical asymptote on the y-axis and that it goes through the point 1 comma 0. And this is clearly true about any logarithmic function that we say is the parent function here. We'll reconfront that phrase there, but basically I'm going to amend one more point here. If this is the x value b, then we would say that the point b comma 1 would be on this graph. But we get this graph that looks like, essentially this all of the time. So what we're going to be confronting here in this video is, what if we have a function that is instead a times log base b of x minus h plus k. And essentially what you would see here is that we're admitting that these logarithmic functions are just transformations of the parent function, where we've seen excuse me, we've seen this before, where we have left and right shift, vertical shift, and then also that this a value in front, what it's doing is it's contributing to either vertical stretch or shrink. So I'm just going to write vertical stretch, and oftentimes, it refers to reflection. Excuse me. So what we're going to see here is that if we know how to graph the parent function, and there's this phrase that I come back to here, you notice that when I refer to the parent function, the values of h and k and a are respectively here for h and k 0 and 0. We don't have any h and k, and then our a value out front here is just a 1, no vertical stretch whatsoever. So knowing this, we could say that, well, if I can graph all parent functions like this that have a vertical asymptote here, go through 1, 0, and b1, and then just these flat graphs, then what we can do is we can shift them and stretch them and reflect them. And so in this table over here, what you see here is that we have log base b of x plus c or minus c. And what I want you to understand is that this is on the outside of our function here, this plus c. So this is what I'm referring to over here is this k value, or this loose constant on the right side. And that, of course, is our vertical shift. And if it's plus c, it's going to go upward c units. If it's minus c, it's going to go downward c units. The thing here is, when you have plus c or minus c, and you notice that it manifests itself in here with the x value, this is, of course, what we've often referred to as our h value. And that, of course, is our left and right shift. So one important thing to note here is that they say plus c means it's going to go left c, and minus c means it's going to go right c. So we'd say that, remember that h value is kind of backwards as how it represents itself. And then what you see here with reflection is essentially this. I'll point the negative x out here first. If you make your x value negative, it's a y-axis reflection. So if you make your y value negative, now that's here, it manifests itself out in front, then it's a reflection over the x-axis. And then we have our vertical stretch and shrink. And I'm just going to kind of designate this one as the primary one we look at. It's not often that we look at something like this. And if you do, maybe you can go look it up again. But let's take a look at a couple of transformations here. So we say find the domain of this function right here. And I'd say it would be beneficial to graph it. So here's what we're going to do. We're going to graph the parent. And this is always true with transformations here. We'll graph the parent first. So the parent function, I would suggest, would actually be this function here, log base 4 of x. So I want you to notice what I've done here. I say that this value of h here, this h value, doesn't exist, and I allow my a value to be 1, my k value to be 0 also. So this is the most basic log base 4 of x function. And so I'm going to graph it, and we'll graph it in blue. So really quickly here, and by really quickly I mean like, hey, really quickly, it has a vertical asymptote on the y-axis, goes through 1, 0. Also this, we would say that if we plug in 4, let's make a table here, x, y, x, f of x. We'd say that we had 1 comma 0. If we plug in 4, of course, log base 4 of 4 is 1. So we get 4 comma 1, and we get this graph that looks like this. Grows really slowly, even slower than that probably. So we'd say this graph here, recognizing that really all we have is an h value of 5, and it is a positive 5, even though it looks like a negative 5. That just means that all of the points on this graph, which I should label here 4 comma 1, everything's going to go to the right 5. So when I say everything to the right 5, let's count it off here. 1, 2, 3, 4, 5. This point here would not be at 1, 0 anymore. It would be at 6, 0, since we went 5 to the right of this x value here. And then this 4, 1, we're going to go 5 to the right of that. It's going to be at 1, 2, 3, 4, 5 here. and that's going to be at 9 comma 1 since we went 5 to the right of that x value. And the fascinating thing here is, of course, the asymptote also shifts right 5, and you could deduce here that obviously the x value of the asymptote would have to be at actually 5, like right there at 5, because you started at 0. So we say x equals 5, and underneath this I'm going to write a little thing here. We say, in general, we say x equals whatever the h value is here. Because if you're going to start at 0 and you shift left and right 5, of course, the h value is the only thing that could shift our asymptote. If you shifted the asymptote that's vertical up and down, it doesn't affect it. So we say x equals h here, and so we get this new graph, and they're just kind of easy to piece together. So in terms of domain, we can observe here in this case that the domain of this function is not 0 to infinity, but instead it would be 5 to infinity. Or what we're going to write here is that this is the asymptote value, and it's completely reflected by the h value of a logarithmic function. So what I can say is, if that's the case, then without making a graph, perhaps, we could take a look at this next function here. We say log base 4 of x plus 3. What I want to indicate here is that our h value is -3. So if we were to kind of visualize this here, we would say that our parent function would run this way, and it'd look like this, and this would be x equals 0. This would really just be shifted left 3, and we could say that its new vertical asymptote would be x equals -3, but it would still be a similar graph. And so its domain, we could say its domain by observation is going to be this. It's going to be -3 to infinity. Now, that's by observation. What I want to point out here is this. Excuse me. Our original logarithmic parent function only has a domain, and maybe I'll switch colors here, of 0 to infinity, not including 0. And the reason why is because when you talk about a logarithmic function here, what can we plug in for x? This cannot be negative, and it cannot be 0, nor 0. Let's pretend I wrote neither. Okay, so neither negative nor 0. But because if you rewrite this, you're saying b to the what power here comes out to be like -4. And like you can't do that with an only positive base. Or what if I said b to the what power equals 0? You cannot raise b to the power of something and get 0. You just can't do it. So what we're saying here is that it only exists for non-negative values that are not equal to 0. So what's in here has to be an x value, and it has to be greater than 0. So we would say that let's write this down. The argument of the log, that's the inside part right here, must be positive. And so it's good to make the graph of this. You could totally find the domain by making the graph, and honestly, it's good practice. Let's just say here, though, without making this actual graph, how could we algebraically find the domain of this? And the rule is this: we'd set the argument greater than 0, solve for x. And so what we're going to do is we're going to take x plus 3 here. We're going to say x plus 3. We have to have a positive value. Okay, so here's the deal. If we solve this, we subtract 3, we get x is greater than -3. So this right here we're going to designate is our domain, and that of course we could, it's almost in set builder notation. We would say all x values such that x is greater than 3 here. But we'd say, of course, that's the same domain that we identified visually. So domain of logarithmic function, always where the argument is positive. And sketching these things, well, just sketch the parent function first and then we'll transform it. Cheers.